Welcome, deep divers. Today, we're plunging into a field that's really reshaping how we interact with technology, natural language processing,
Or NLP, yeah.
NLP for short. And at its heart, it's about computers, well, working with human language.
Right. Everything from pretty simple stuff, like just counting how often words appear,
Mm.
to the really huge challenge, which is getting computers to genuinely understand what we say and write.
It's this fascinating mix, isn't it? Linguistics and computer science kind of rolled into one,
Absolutely. And when we say natural language, we mean human languages, English, Spanish, Japanese, the ones we speak naturally.
as opposed to, say, Python or C++L.
Exactly. Those are artificial languages designed with explicit rules. Natural languages just evolved. They're fluid, complex, and really hard to pin down with rigid rules.
Which is the big problem for computers.
That's the core challenge.
Yeah, okay. So for this deep dive, our main guide is Natural Language Processing with Python by Bird, Klein, and Loper, an O'Reilly book
A foundational text, really. It's very practical.
built around Python and the Natural Language Toolkit, NLTK.
Right. NLTK is this open source library that gives you the building blocks. The book shows you how to use it, not just the theory behind it.
So you can actually build things.
Exactly. Our mission today, then, is to sort of unpack how computers try to bridge that gap with human communication
Pulling out the core ideas, the surprising bits from the text.
and give you a shortcut, hopefully, to getting your head around this field. You'll see what NLP covers, but also why it's so crucial now.
The building blocks of NLP.
Okay, so let's start with the big why. Why is NLP so critical today? I mean, think about the sheer amount of information out there locked up in text on the web.
Is overwhelming.
Totally. And search engines are great, but they often struggle with nuance, right? Like if you ask, what tourist sites can I visit between Philly and Pittsburgh on a tight budget?
Yeah, that's not just keywords. That needs interpretation.
Exactly.
And to answer that kind of question, a computer needs a whole range of NLP skills.
Like what?
Well, information extraction, pulling out the specifics like locations, budget limits.
Okay.
Then inference, drawing conclusions that aren't explicitly written down.
Right.
And summarization, boiling down lots of info into a useful answer.
Mm-hmm.
It's way beyond keyword matching.
And one of the huge hurdles, as you mentioned, is just how ambiguous language is. Take word sense disambiguation.
Oh, yeah.
The book uses he served the dish. What does serve mean? Help with food, hold office,
Wow.
tennis.
A dish,
Yeah.
a plate, the meal itself,
Mhm.
a satellite dish.
We just know from context.
All right.
But the computer, it sees all those options at first.
That ambiguity is a massive challenge, especially, for machine translation.
Right.
Think about translating. The thieves stole the paintings. They were subsequently found.
Okay.
If you translate they into French, is it the masculine thieves or the feminine paintings?
You need to know what they refers to.
Exactly. That requires understanding the meaning, not just swapping words. Modern systems try to figure this out by looking at huge amounts of translated text, finding statistical patterns.
So they learn from examples, not just grammar rules.
Pretty much. It's more about alignment in massive parallel text these days.
Interesting. And it's not just translation. There's also this idea of recognizing textual entailment, or RTE.
Hmm.
The example given is, David Galinkin is the editor or author of 18 books. Hypothesis. Galinkin has written 18 books. Is that true?
Not necessarily. He could be the editor of all 18.
Right. So to get that right, the system needs background knowledge. It needs to know what editor versus author actually means.
And that really highlights the current limits. NLP systems are amazing, but they still struggle with genuine common sense reasoning, deep world knowledge.
So they're using clever tricks for now.
The source calls them superficial yet powerful techniques. They work well for specific tasks, but it's not quite human-like understanding yet. That's still the goal.
Okay, so the why is clear language is complex. We need help. How do we actually do it? What's the toolkit?
Well, Python is often the go-to language.
Why Python specifically?
Several reasons. It has a relatively shallow learning curve. Yeah. The syntax pretty transparent, easy to read.
Good for complex stuff.
Right. And it's got great tools for handling strings, which is obviously key for text. Plus, it's interpreted, so you can play around interactively.
Makes experimenting easier.
Definitely. And things like object orientation for reusable code, dynamic typing for quick development. It just fits the NLP workflow well, widely used too.
And sitting alongside Python is the Natural Language Toolkit, NLTK.
Yes, NLTK. It's this fantastic open source library. Think of it as the infrastructure for building NLP programs in Python.
What does it give you?
It gives you basic building blocks for language data, standard ways to do common tasks like tagging words or classifying text, and ready-made components you can combine for complex problems.
So it saves you from reinventing the wheel.
Absolutely, it streamlines everything.
The book lists a bunch of NLTK modules, things for accessing text collections, breaking text into words, tagging parts of speech, classification, parsing sentence structure, even evaluating models.
It's a pretty comprehensive toolkit, a workbench for NLP, really.
Okay, we've got the tools. Let's talk about computing with language, treating text as raw data. How do you start?
Well, you can just fire with the Python interpreter, maybe use IDE.
And start typing?
Pretty much. NLTK even comes with some built-in texts, like in nltk.book. You can load Moby Dick text 1 instantly.
Okay, so you have the text. What can you do with it?
You can treat it essentially like a list of words in Python.
Ah, so standard list operations work.
Exactly. Find the total word count with len, text 1. Count how many times a specific word appears, like text1.count heaven.
And you can access specific words or sections.
Yep, using indexing and slicing.
Yeah.
Text 4173 gets you a specific word, or text 516715.16735 pulls out a whole phrase. Basic but powerful.
Now, where it gets really insightful is looking at frequency distributions, like a word tally, right?
Exactly, but more sophisticated.
Mm-hmm.
NLTK's Frequency function is great for this.
So you could find the most common words in Moby Dick.
Easily. Frequency text 1, and then look at the top 50. You'll see common words, but also lots of punctuation commas, periods they get counted to.
And you can check specific words, like whale.
Yep, Frequency 1 whale. Turns out it appears 906 times.
Wow, that's a lot of whale.
It is Moby Dick. But beyond simple frequency, you can use conditional frequency distributions,
What's that for?
comparing word usage in different situations. Like, how does vocabulary change across different genres? Or even different languages?
Okay.
The book shows a cool example of how word lengths are distributed differently in languages like Ibibio versus German versus Inuktitut. Subtle patterns emerge.
And NLTK gives you access to lots of pre-packaged text data, these corpora.
Yes, loads. And Gutenberg corpus has classic books.
Like Jane Austen's Emma.
Right. The Brown corpus is really useful because it's grouped into 15 genres: news, adventure, religion.
So you can compare language across genres.
Exactly. Brown.words. Categories news just gives you words from news articles.
Yeah.
Then there's the Reuters corpus news stories, but with overlapping topics, which is more like real-world data.
So corpora come in different structures.
Yeah, the book outlines common ones. Isolated texts, categorized like Brown, overlapping like Reuters, or even temporal, like tracking U.S. inaugural addresses over time.
Different structures, but fundamentally.
They're collections of texts, often with useful metadata, ready for analysis.
All right, we've got the tools, we've got the data. Now, how do we prepare raw text? This idea of sculpting text.
This is crucial, and key tool here is regular expressions.
Regex. Sounds intimidating.
They can be, but think of them as a powerful mini-language just for finding patterns in text, super precise.
How are they used in NLP?
All sorts of ways. The book has a neat example showing how regular expression could mimic the old T9 phone input, matching words like gold or whole based on number sequences. The point is, you use special symbols to define what you're looking for repetitions, plus alternatives, specific characters, D for digit, grouping. It's pattern description.
Not just exact word matching.
Right. And NLTK actually extends this. It has special regular expressions that can search across tokenized text, so patterns spanning multiple words.
Like finding a man, or maybe phrases ending in a specific word.
Exactly. Very useful for linguistic patterns.
Okay, besides finding patterns, often we need to simplify words, right? Get them down to their root form.
Yes, that brings us to stemming and lemmatization.
What's the difference?
Stemming is usually a rougher process. It often just chops off common suffixes based on rules.
So pons becomes pond.
Hopefully.
Yeah.
But it might also turn is into I or basis into basis. Sometimes it creates things that aren't even real words, like distribute. It's heuristic.
Algorithms like Porter Stemmer do this.
Porter and Lancaster are common ones. But yeah, it's not always pretty. It's fast, but crude.
So if stemming is crude, what's the alternative?
That would be lemmatization. It's smarter.
How so?
It uses a dictionary, like WordNet.
Yeah.
It only removes an ending if the result is a valid word in the dictionary.
So it checks.
Yes. So NLTK.WordNet lemmatizer turns women into woman, which is correct. But it leaves lying as lying, because that's its actual form, not derived from lie.
Does that make it better?
Generally, yes, more accurate. But that dictionary lookup makes it slower than stemming. Trade-offs.
Got it. And just quickly, you mentioned text as a list of words. That difference between a string and a list is key.
Absolutely fundamental. A string is just a sequence of characters. Tokenizing it into a list of strings, a list of words or symbols, gives you that granularity you need to work with individual linguistic units. It's often step one.
Okay, text sculpted, tokenized. Now let's give those tokens some meaning, or at least a role. Part of speech tagging.
Exactly, POS tagging. Classifying words. Is it a noun, NN,
Yeah.
a verb, VB8, an adjective, JJ? It's usually the next big step after tokenizing.
Why is this so important?
Well, it helps predict how unknown words might behave. It lets you analyze word usage patterns. Are nouns more common in this text? And it's crucial for things like text-to-speech, where pronunciation can depend on the part of speech.
How do we learn these tags? From tagged corpora?
Yes, data sets like the Wall Street Journal corpus, where experts have already tagged each word. You get data like Pierre, NNP,
Yeah.
Vinken, NNP, proper nouns.
And you can analyze this data.
Definitely. You could use conditional frequency distributions again. Maybe find words that can be both a past tense verb, VD, and a past participle, VN, and then look at the words around them to see what context triggers which tag.
So how does automatic tagging work? How does the computer learn to do it?
There are several methods. You could use a regular expression tagger, simple rules like if a word ends in S, tag it as a plural noun, NNS.
Rule-based.
Right. Or a basic default tagger just assigns the most common tag, maybe noun and NN, to any word it doesn't recognize. It's a fallback.
More sophisticated methods.
Then you get into statistical models, n-gram taggers. A unigram tagger looks at the most likely tag for that specific word based on the training data.
Okay.
A bigram tagger looks at the current word and the previous word's tag. A trigram looks back 2 tags. They get more context.
Do they get confused?
They can. So they often use back off. If the trigram model isn't sure, it falls back to the bigram, then maybe the unigram, then the default tagger. It combines them.
Any other approaches?
There's also transformation-based tagging, often called Brill tagging. It starts with simple tags and then learns a set of repair rules, like change tag NN to VB if the previous word was TO. It learns to fix common mistakes.
Interesting. And fundamentally, how do we even decide if something is a noun or a verb? What clues do we use?
Linguists look at different things. Morphological clues are about the word's form endings, like ing, often mean it's a verb form.
Like word shape.
Exactly. Syntactic clues are about context. Where does the word usually appear? Adjectives often come before nouns or after verbs like be.
Position matters.
And then semantic clues, which relate to meaning. A noun is the name of a person, place, or thing. But meaning is trickier to formalize for a computer than shape or position.
Okay, we can tag words. What about classifying whole chunks of text, like spam filters or sentiment analysis?
Right, that's supervised classification. Basically, teaching a computer to assign the correct label, spam, not spam, positive, negative, to a given input.
And it learns from examples.
Exactly. You train a classifier using a training corpus where you already know the right labels. The classifier learns the patterns associated with each label.
How does it learn the patterns? Through feature extractors.
Yes, that's crucial. You need to tell the classifier what aspects of the input it should pay attention to. These are the features.
Like the name gender example.
Perfect example. A function gender features, word, might return a dictionary. For Shrek, maybe just last letter.
Simple.
But you can make it smarter. Suffix to, she for names ending in she or first letter. You design features that you think are predictive.
And for classifying documents, like movie reviews.
Features are often about word presence. Does the review contain the word brilliant? Does it contain terrible?
Ah, like the Siegel versus Damon example.
Exactly. Siegel appearing makes a negative review much more likely. Damon suggests positive. Using Python sets to check for word presence is very efficient here, much faster than checking lists for large texts.
Okay, so you have features. What kind of classifiers use them? You mentioned decision trees.
Right. Decision trees are like flowcharts. They ask a series of questions based on the features. Does it end with A? Does it contain excellent to arrive at a label?
They sound easy to understand.
They are. Very interpretable. But they can sometimes struggle if the relationships between features are really complex.
What else is there? Naive Bayes classifiers.
Yes, a very common probabilistic approach. It calculates the probability of a label given the features it sees.
Why naive?
Because it makes a simplifying assumption that all features are independent of each other, which often isn't true in language.
Does that cause problems?
It can lead to double counting, where related features get too much weight. And there's the zero counts issue. If it never saw a specific feature with a specific label in training, it might think it's impossible. You need techniques like smoothing to handle that.
Are there classifiers that don't make that naive assumption?
Yes, things like maximum entropy classifiers, often called maxent. They're also probabilistic, but use optimization techniques to find a model that fits the observed data frequencies without assuming features are independent unless necessary. They try to be fairer in distributing probabilities.
Okay, lots of options. But how do you know if your classifier is any good? Evaluation must be key.
Absolutely critical. You cannot evaluate on the same data you trained on. The model might just memorize the answers.
So you need separate data sets.
Yes, a training set to build the model. A dev test, or development, set to tune your features and model parameters. And a final, untouched test set for the real performance measure.
And what do you measure? Accuracy.
Accuracy is one thing, but often not enough. We use precision. Of the items the classifier labeled positive, how many were actually positive, and recall. Of all the truly positive items, how many did the classifier find?
Precision and recall. Sometimes they trade off.
Often, yes. So we also use the F measure, which is the harmonic mean of the two, giving a single score. And confusion matrices are great visual tools.
What do they show?
They show you exactly where the errors are happening. Is your classifier confusing label A with label B? How often? It helps you diagnose problems.
Okay, moving beyond just classifying, what about extracting structured data from text, like finding company names and where they're located?
Right, that's information extraction, taking unstructured text and pulling out specific organized information.
How does that typically work? Is there a process?
Yes, usually an information extraction pipeline. The book shows a diagram. Raw text sentences, tokenized sentences, tagged sentences, chunked sentences of relations.
So it builds up step by step. What's chunking?
Chunking is about identifying short phrases or chunks that represent meaningful units. Noun phrase chunking, NP chunking, is common, finding chunks like NP the board or NP President Obama.
How do you define these chunks?
Often using chunk grammars, which are like regular expressions, but they operate on the POS tags, not just the raw text. A rule might say an optional determiner followed by 0 or more adjectives followed by a noun makes an NP chunk.
Okay. And related to that is named entity recognition, NER.
Yes. NER goes further than just finding noun phrases. It identifies and classifies specific named entities.
Like people, places, organizations.
Exactly. Georgia Pacific Corps is an organization. President Obama is a person. Murray River is a location. June is a date. $500 is money. Also things like percent, facility, GPE, geopolitical entity like U.S.
Sounds powerful. What are the challenges?
Well, lists of no names, gazetteers are never complete, so new entities are hard. And ambiguity is a killer. Is May a month or part of a name like Theresa May? Is Yankee modifying something, or is it the name of the team, an organization? Context is everything.
All right, so we can extract chunks and entities, but what about the overall structure of a sentence? Language isn't just bags of words or chunks.
Precisely. The book highlights this idea of linguistic data and unlimited possibilities. We don't just repeat sentences we've heard. We make grammaticality judgments. We know colorless green ideas sleep furiously is grammatically weird but structured, while sleep ideas green furiously colorless is just word salad.
And we understand sentences we've never seen before, even really long ones.
Which shows that simple models like n-grams, while useful for predicting the next word, fundamentally miss the deeper structure. They can generate plausible short bits, but fall apart quickly because they don't understand syntax.
They can't handle things like coordinate structure, like NP, the worst part and the best part, being a valid noun phrase because both sides are noun phrases.
Exactly. Syntax captures those hierarchical rules.
Which leads to constituent structure and phrase structure trees.
Right. The idea that sentences break down hierarchically. An S sentence might be an NP, noun phrase, plus a VP, verb phrase. The VP might contain a V verb and another NP.
Like those tree diagrams from school?
Pretty much. And critically, unlike chunking, which often has a fixed depth, these trees can be arbitrarily deep, allowing for complex nested structures like the dog that chased the cat that ate the mouse.
How do we define the rules for these trees?
Using a context-free grammar, CFG, it's a formal way to write down the rules to productions like SNP-VP or NP-det-N.
And CFGs allow recursion.
Yes, a rule can refer back to itself, example NP-PPP, which is how you get those arbitrarily deep structures. That's key to modeling human language's creativity.
So you have a grammar. How do you apply it to a sentence? Parsing algorithms.
Correct. You need an algorithm to figure out which rules apply and build the tree for a given sentence.
What kinds are there?
A simple approach is recursive descent parsing. It works top-down, trying to match grammar rules to the input. But it can be inefficient, get stuck in loops with certain grammars, and struggle with ambiguity.
Is there a better way?
Yes. Chart parsing is much more common for real-world NLP. It's a dynamic programming technique.
Meaning?
It builds up a table, the chart, or WFST, of all the valid constituents it finds for substrings of the sentence. It stores results, avoids redoing work, and handles ambiguity much more gracefully by potentially storing multiple parses for the same substring.
And ambiguity is common in syntax.
Oh, absolutely. Syntactic ambiguity is everywhere. The classic, I shot an elephant in my pajamas. Who's wearing the pajamas?
Elephant or me.
Exactly. The prepositional phrase, in my pajamas, can attach to elephant, modifying it, or to shot, modifying the verb phrase. And that's besides lexical ambiguity, where words themselves have multiple possible parts of speech, like dog being noun or verb.
Okay, CFGs are powerful, but maybe a bit rigid with just atomic labels like NP, VP.
They can be. That's why we move towards building feature-based grammars.
What's the idea there?
Instead of just NP, think of it as NP with associated features like NP, NUM, plural, gender mask. Grammatical categories become structures like dictionaries, where features take values.
How does that help?
It's great for handling things like syntactic agreement. You can write a rule like SFNP, NUM in, VP, NUM.
What is NDO?
It's a variable. It forces the NUM number feature of the sub NP and the verb VP to be the same value. So dog barks works, singular, but dog bark fails because the numbers don't unify. This dogs would result in NUM fail.
Clever. How are these feature structures represented?
Often as graphs-directed acyclic graphs or DAGs. An interesting aspect is structure sharing, or reentrancy, where multiple feature paths can point to the exact same value structure, saving space and representing shared information.
Like two people sharing the same address feature structure.
Exactly, and the core operations on these are subsumption and unification.
Subsumption.
It means one feature structure is more general than subsumes another. NUME she subsumes NUME she, PER3.
And unification.
That's combining the information from two feature structures. If they're compatible, you get a new structure with all the info. If they conflict, like trying to unify NUMB as ESG and NUMPL, unification fails. These are the basic computational steps.
And these feature grammars can handle more complex things.
Yes, phenomena like verb subcategorization, what kind of objects a verb takes, complex constructions like inversion, and crucially, unbounded dependencies.
What's that?
Like in, who do you think Kim likes? The who is the object of likes, even though they're separated by do you think Kim. Feature grammars provide mechanisms to track these long-distance relationships.
This is getting deep. From structure, we finally arrive at analyzing the meaning of sentences. Computational semantics.
The ultimate goal, perhaps. How do computers process meaning?
Is it about translating to database queries?
That was an early idea, but it's too database specific. The focus shifted to representing meaning in a more general logical form.
Using what?
Truth-conditional semantics is a key idea. Define the meaning of a sentence by specifying the conditions under which it would be true in some situation or world model.
Relating language to the world.
In a formal way. It connects to historical ideas too, like the Turing test. Can a machine converse so well you can't tell it's a machine? That's a behavioral test of understanding.
And what logic is used for this representation?
First-order logic is often a good starting point. You have predicates and arguments. Angus walks becomes walk. Angus sees birdies, see, Angus, birdie.
Okay.
And critically, you have quantifiers. Exist X means there's just some X such that. And all X means for all X.
How does that help?
You can represent complex sentences like every dog disappeared as all X, dogs disappear X. It captures the logical structure precisely.
How do you build these logical forms from the sentence structure?
That's where tools like lambda calculus come in. It allows you to define the meaning of words and phrases in a way that lets them